El salón de seminarios cuenta con un sistema de grabación de videoconferencias para nuestros expositores y transmisión por streaming desde nuestro portal de internet. Nuestras butacas están equipadas con un moderno sistema de asientos plegables y base con riel deslizable. Por respeto a los asistentes, evita hacer ruido al levantarte y no introduzcas alimentos. Gracias por tu atención.
Buenos días, muchas gracias por estar presenciales y en línea. En unos minutitos, un minutito o dos empezamos. Una disculpa por la demora. Ahora sí, buenos días. Una disculpa por la demora en el retraso. Mi nombre es Rosa María Flores, yo soy subdirectora de Hidráulica y Ambiental. El día de hoy tenemos la presencia de un destacado profesor investigador de la Universidad de Tsinghua, el profesor Dehua Liu, quien nos va a hacer el favor de dictar una conferencia que se llama Advances on Biofuels and Other Environmental Issues at Tsinghua University, Collaboration Expectations with UNAM. Pero antes vamos a tener, nos acompaña en el estrado la doctora Rosa María Ramírez Zamora, que es la directora del Instituto de Ingeniería, y el profesor Eduardo Bárcena, de acá de la universidad, destacado profesor investigador y emérito. Le pido a la doctora Ramírez si me da unas palabras, por favor.
Gracias, doctora Rosa María Flores. Thank you very much, Rosa María Flores. Thank you very much also to our Professor Dehua Liu. This is the third time he's visiting us in our institute. I also would like to thank Professor Eduardo Bárcena for being here. I also thank, and you're very welcome, all the people that is with us in this Salón de Seminarios, Emilio Rosenbluth, and all the people that is connected for this important, very interesting lecture. I hope that all your expectations and maybe more will be obtained from this lecture, and I hope also that most of people, the young people that's here with us, will be also at 4 o'clock. We had another meeting with Professor Liu that will be very important for you to try to see all the options of collaboration with the University of Tsinghua, especially with the Professor Liu, and I hope you'll be very successful in your lecture, Professor Liu. Thank you very much.
Muchas gracias, doctora Ramírez. Y ahora le pido al doctor Eduardo Bárcena García. Él es investigador de mérito de la Universidad Nacional Autónoma de México, ha sido director de la Facultad de Química, es secretario académico de investigación de la misma facultad, y bueno, su currículum es bastante amplio, es un orgullo de la UNAM, y también si nos quiere dirigir unas palabras, por favor, acerca de este evento. Muchas gracias.
Claro. Bien, pues muchas gracias, muy buenos días a todas y todos. Yo realmente agradezco mucho a la doctora Rosa María Ramírez Zamora que me haya invitado a esta conferencia tan relevante y tan importante. El doctor Liu va a tocar un tema que es sin duda de mucha actualidad, o varios temas, ¿verdad? Porque el asunto ambiental cubre muchas aristas, ¿verdad? Muchos requerimientos, pero sin duda es una temática que está requiriendo urgentes acciones. Entonces, creo que su visión desde un sitio tan avanzado en ciencia y tecnología como es China y como es su universidad, pues va a ser muy relevante. Así que es una gran oportunidad para los jóvenes, una gran oportunidad para los ya un poquito mayores, ¿verdad? Tener esta posibilidad, ¿no?, de establecer en un futuro colaboraciones con esta importante institución. Así que, nuevamente, muchas gracias, Dr. Liu. Thank you very much for being here with us this morning.
Muchas gracias, Dr. Bárcena. Even though your lecture is going to be in English, I'm going to introduce you in Spanish because the persons who are attending are in our language. I'm sorry. El profesor Liu, él es, bueno, un gran amigo de la Universidad Nacional Autónoma de México. Bueno, creo que están muy jovencitos, muchos de los que están aquí no lo recuerdan. Él estuvo ya con nosotros en el año 2016 y 2017. Con él es con quien hicimos los primeros intentos de hacer un convenio con la Universidad de Tsinghua. Por si no lo saben, la Universidad de Tsinghua está en Beijing y es la universidad más grande en temas de ingeniería en China y es la número 16 a nivel mundial. Entonces, tener nexos con esa universidad es muy importante. Él en particular es de la Escuela de Química de esa universidad. Y gracias a esos encuentros que tuvimos en 2016 y 2017 en particular, que en este recinto tuvimos un seminario donde estuvieron participando 11 institutos, creo que fueron 11 institutos de acá de la UNAM hablando de temas de biocombustibles, fue el que detonó que posteriormente tuviéramos el convenio que se firmó en 2018 y que está por renovarse nuevamente este año. El profesor Liu es ingeniero químico de la Universidad de Tsinghua. Él cuenta con investigaciones muy importantes en el área de recursos renovables e ingeniería en bioenergía, en particular tecnología de fermentación, ingeniería de bioreacciones, ingeniería metabólica, y ha publicado más de 200 artículos a nivel internacional con factores de impacto importantes. y ha presentado más de 60 patentes, de las cuales 50 han sido concedidas. Y además ha hecho la transferencia tecnológica de varias de estas patentes, todas, no todas, pero la mayoría en temas de biocombustibles y temas afines. El profesor Liu, además, si ustedes quieren hacer contacto posteriormente con él, está abierto a comunicación. En la tarde tendremos otro evento en este mismo recinto a las 4, en donde se hará la presentación del programa para jóvenes científicos que tiene el Ministerio de Ciencia y Tecnología de China, donde el profesor Liu nos va a hacer presentar este programa y ver la forma en que jóvenes académicos pueden hacer estancias en China bajo este nuevo programa académico. Bueno, si leyera todo el currículum del doctor Liu, nos podríamos estar aquí horas. Creo que con esta breve semblanza del tipo de productos que el doctor Liu hace, más lo que nos va a decir en esta charla, serán más que suficientes para su presentación. Les agradezco mucho a los miembros del Presidium habernos acompañado. And now we are going to start with the lecture, Professor Liu. We are going to leave you here in this scenario. To give your talk. Thank you very much. Un aplauso, por favor.
So this is.
Yes. No, the other side.
Oh yes.
And
Yes.
okay.
Yes.
And with this, it should be the pointer.
Yes.
This one.
Okay.
¿Puede tener control acá? Well, you're going to see that.
Okay.
¿Sí?
It's okay. Well, I can.
Bueno,
It's
not,
okay.
no se ve, pero
This.
sí.
Yes. Yeah.
Ahí está.
Okay. Thank you.
Thank you very much.
Thank you. It's my pleasure. Okay. Good morning, ladies and gentlemen. It's my very high pleasure and honor to have the opportunity to visit UNAM again. Actually, I remember this is my third time or fourth time to visit UNAM, and because of the pandemic, we stopped the connection for a few years. So this time, I was invited by the AICHE, the American Institution of Chemical Engineering. They organized the annual conference in San Diego. So I contacted Rosa. I say if I can have the honor to visit you again. So I thank you, Dr. Rosa and the professor and all you guys to come here. At the beginning, Dr. Rosa told me maybe you can talk about the advanced biofuel technology in your institution, and so I say maybe I can talk a little bit wide, not only for the biofuel, maybe for the bio-based materials, is so-called biorefinery, biomanufacture. You know, so far the fossil carbon resources, the petroleum, natural gas, the coal, is so important for our living, our social progress. But the problem is the carbon already fixed underground from the atmosphere. But now, as the so-called civilization, people dig out and burn and degraded to the CO2 back to the atmosphere again. So this is now the key issue for the environmental, for the climate change. So now we have to a little shift from the fossil carbon utilization into the biocarbon, the biomass. So if we use the biomass, of course, the fossil resources, the fossil carbon was the ancient biomass, was the ancient atmosphere CO2. And now, if we use theoretically for the chemistry professors, we can use the biomass totally replace the fossil carbon. So this is why people talk the concept of the biorefinery, to utilize the biomass to produce the fuels, energy, materials, and so on. So, of course, the biorefinery is so huge concept for the industry, for the academic, for the everyone. So now I will talk about the research and development and the industrialization of biorefinery technology for bio-based materials and bioenergy. And on behalf of my group people, so including Professor Wei Du, Xuebin Zhao, and Chen Jin, Dr. Chen Jin, and myself. So the contents, I will talk the 4 outlines. Why? The first is about the the design and the optimization of bio-based polyols synthesis route. You know, the polyols is a very important monomer for the polyesters, polyurethane, and for the textile, for the plastics, and so on. Most of the polyols, including the C2 to C6 polyols, was manufactured industrially, manufactured from the fossil, from the natural gas, petroleum, and coal. Now we want to use the chemical, it was the biochemical process to manufacture the polyols. So first, we developed a new chassis for the next generation of industry biotechnology. I mean, we developed a new host bacteria, which is a good host bacteria can be used as the host to convert the different chemicals. So the which is the Webinar lactease. This bacteria. Oh, I'm sorry. Yeah. Sorry. This bacteria have the advantages like this. It's the known fastest growing bacteria, and it's tolerant. It's has the resistant to the haptonicity, which is very suitable for the, even can be in the open culture for the cultivation, because it's easy to control the contaminant for the other bacteria, because it's tolerant to the haptonicity. And another important is this bacteria is also biosafe. You know, some bacteria is not so safe. It's dangerous for the some disease or something. Yeah, and we modify the modeling, the metabolic modeling, metabolic network model. So the modifying, including more than 1,000 metabolites, very close to 1,000 genes, and so on. So including according to the modification and the calculation optimization of the metabolic network model, so show such a bacteria has significant advantages in biosynthesis. For example, compared with the E. coli, which is the most used for the synthetic biology host. So this new bacteria is even more advantage over the E. coli. You can find the tablets, the succinate, lysine, 1,3-butanediol, 1,3-propanediol. The cumulate is much higher than the E. coli, and we also developed a efficient gene editing tools. If without these editing tools, it's difficult to modify, to aid in the engine for this. And also the next, another important work on the polyols, we developed industrial strains which efficiently utilize various carbon resources, including the glucose, sucrose, xanose, esters, molasses, and even some C1 substrates. For example, the methanol, even the methane can be utilized to synthesize the 1,3-propanediol. 1,3-propanediol is a very important monomer, can be used for the polymerization of polyester. The soft drink tuber is the bottom is a PET. PET is a polymer between the ethylene glycol with the PTA. But if we use the PDO, 3 carbon atoms, the diols, it can also use for because it's diols, can be used for the polymerization. Get the plastic says PTT, the polyester. The PTT, they say, is the base textile fibers. And so we developed the 3 pathway for the production of PDO. So before the pandemic, when I came here, I also talk about this pathway from the glycerol. Glycerol is the bioproduct of biodiesel. The biodiesel is use the glycerides, vegetable oil, animal fat to transesterification to get the biodiesel. Get the byproduct is the glycerol. So we first convert the glycerol to PDO by the fermentation. But the PDO demand is so huge. Only use the glycerol is not sufficient. So we developed the different process. We developed the 3 process pathway for the production of the PDO. This already commercialized. And another, the 2 process, the pathway from the different carbon resources. So you can find when we fermented used only the glucose, the accumulation of the PDO came more than 110 grams per liter. And if we use the hydrolysate, the mixture of glucose and xanose as a co-substrate, also the PDO can reach the fermentation title can reach 100 grams per liter. This was the public papers. You can see, find more details. We already commercialized the process in China. So we actually already improved the 3 generations of the technology. The first generation is only used the glycerol, the pure glycerol. Use the Klebsiella, the bacteria. It's a wild bacteria, more used for the production of the PDO, and which already commercialized. The capacity is 20,000 tons per year, which was put into running in the year 2015. And Then we modify the bacteria and also use the one I just mentioned is the best one. We can directly use the crude glycerol from the biodiesel. You know, the crude glycerol, we even import the glycerol from Brazil. They contain the glycerin concentration is about 85%, but they contain also the salt. The sodium chloride is about 3.5 to 6%, and also roughly 1% of methanol, and also some months. So we can directly use the crude glycerol, use the modified bacteria to produce the PDO. Also commercialized, the capacity is 15,000 tons per year. The company is Tsinghua Smart Biotechnology, which was created by myself. You know, in China, we have the policy to encourage the professors, researchers to create the startup company, yeah. And the third generation, we can use the different various carbon resources, glucose, sucrose, fiber hydroxide. Also use the best one, the nitrogens, and also use glutamation. Is usually used for the amino acid produce. Yeah, we use these both can use to produce also already commercialized with the capacity 20,000 tons per year. Use the glucose. Start from the corn. Get the oil, the protein, and then the pure starch. Liquefaction to the sugar, and then fermentation to this. Yeah. And also we research the convention, the biosynthesis of 1,5-pentanediol. I say that we focused on the diols. The pentanediol is also widely used in the polyester, polyurethane, plasticizers, Lincoln coating. So far, the market demand is more than 100,000 tons, and the value of output is more than $500 million. All the commercial supply of 1,5-PDO was manufactured from the petroleum, the chemical industry process. And so far, nobody found a nature microbial pathway to produce the 1,5-PDO. So we, not only our group, other groups globally also research the pathway. We can find totally five pathway from the glucose to the 1,5-pentanediol. And we have the optimization, comparison each one, and finally to identify which one is the best. And this is the so-called unnatured pathway. Yeah. So we did the modification, knock out some genes, and enhancement of some metabolite step, and then finally we already got the by the small risk. The shake braskers, the fermentation, we got the pentanediol title is about 10 grams per liter. And now we are trying to demonstrate the process in a pilot plant in the fermenters. And so far we already commercialized the 1,3-propanediol, 1,3-propanediol. We also developed the other diols, the 1,2-propanediol, 1,4-butanediol, and the 1,2-butanediol. I mentioned the 1,5-propanediol and also the 1,6-hexanediols, also including the ethylene glycol, the 2. So from the C2 to 6 diols, we already engineered the bacteria can carry out the fermentation. But so far only the 2,3-butanediol, 1,3-propanediol already commercialized. 1,5-propanediol is under the pilot plant testing, and the others we will promote again and again. This is for the diols. So the second, I will introduce about the enzyme catalyzed conversion of fats and oils to high-value products. The fats and oils, Professor Yu researched the microalgae accumulation to produce the fats and the vegetable oils. So how to utilize the vegetable oil. And we also, one of my colleagues, the Professor Wei Du, she is focusing on the subject. So, and the utilization of the conversion of the fatty acid and the glyceride, the key issue is the enzymatic isolation reaction. And we researched the mechanism, and for example, the lipase KB has a hydrophilic pocket, and the activity and the selectivity for the fatty acid donors or acceptors are affected by various factors. So we published many papers about this, the mechanism research. And also, when the enzyme catalyzed the conversion, the isolation, the intermediate potential, the enzyme will combine with the substrate and then to form the intermediate. The intermediate potential energy of the enzyme substrate transition is the transition state. The state will also affect the enzyme selection. So this is the research about the mechanism. And then we also researched the enzymatic OPO synthesis. OPO is the glyceride, and the one fatty acid chain is oily fatty acid, and the other is also 2 oily fatty acid chain, and the middle is the palm fatty acid. So this is very important for the baby nutrition. Some medicine research and people explain, reveal the importance of the OPO. So people in China, I don't know here, in China, some company wanted to get the OPO for the additives of the baby milk powder. So we researched for this project and also tried get the contract with some nutrition company. So the research on the catalytic properties of non-homogeneous and non-aqueous enzymes featured on the enzyme catalyzed the conversion of oils and fats to the high-value product, just like this, and revealing the mechanisms of enzyme activity, selectivity, and isolation. More than 10 products synthesized, such as the oleic acid glycerides, 1,3-glycinol diglycerides, and also the OPO, OPL, MLACT, based on the different substrate and different routes. So we published a series, some papers of this, and the other research is about the bioenzyme catalyst, the high efficient bioenzyme catalyst development. So, and the first research is about the lipase expression. So we effectively expressed in E. coli and pitcher, the yeast, to express the BTL2 lipase, which can be used for the biodiesel production catalyst. And also we also researched the carrier for the immobilization of the enzyme. So finally, we developing high efficient biological enzyme catalyst with different properties, and also a novel single crystal ordered macropolus morphs created by the hard temperature method and ligand exchange, which is suitable, tolerant to both water and acid. You know, the carrier of the immobilized, for the immobilization of the enzyme, the key issue is to tolerant for the water and acid for the hydrous, the utilization of the enzyme. So also the carrier is a good carrier for the enzyme immobilization. And about this research, we also focused on the including the whole technological solution, including the optimization of technology process factors, and also the equipment, the key issue equipment development for the biodiesel production by enzyme catalyzed. So the enzyme, the lipase, can simultaneously catalyze the 3 reactions during the biodiesel production. One is the transesterification of glyceride with methanol to get the glycerol and the esters, the methyl esters, is the biodiesel. And another reaction is the hydrolysis of the glyceride into the methanol and the fatty acid. The fatty acid can also esterify with the methanol to the methyl esters. So the methyl esters was the biodiesel. So use the chemical process, they can only catalyze the transesterification of the glyceride to the biodiesel. So there is a very strict requirement for the feedstock. The feedstock, the chemically catalyzed process for the biodiesel production, the feedstock should contain as less as possible of the free fatty acid, as less as possible of the moisture. Otherwise, so much of the sulfur be formed, reduce the yield of the biodiesel. So use the enzyme can catalyze the 3 reactions simultaneously. So use the enzyme as the catalyst instead of the sodium mesonate, the chemical catalyst. So the requirement for the feedstock is very wide, and they can catalyze all kinds of the oils, fats to the biodiesel. So we developed a novel process solution, including the technology and the reactor, with a wide suitability to the various feedstocks, and the enzyme lifetime could be extended by 10 times compared with the invention enzyme process. Actually, 15 or 12 years ago, you can find so many published papers focused on the enzyme catalyzed biodiesel production, but nobody commercialized the process. So we research all the process, including the process parameters, optimization, and also the key equipment design. So we commercialized the process. So we already commercialized in China. The first one is located in Hunan, and the capacity was 50,000 tons per year. Directly used cooking oil, which contain more than 60% of the free fatty acid and some moisture, some other impurities. So we directly use the cooking oil, so-called UCO. I don't know, the Mexico City is huge and also should produce many of the UCOs. So UCO, I don't know how about here to connect the UCO to convert to the biodiesel. And that was put into running in the end of the 2006. And then we modified 3 chemicals. These 3 facilities was established for the chemical catalyzed process to produce the biodiesel. We just finished the modification to the process. It's easy, yeah. We just modify the reactors, install a new reactors. The whole process is the same. And also we have we developed membrane facilities to recycle the enzyme. The enzyme can be used for more than 300 cycles. So it is economically competitive with the chemical process. So we modified these 3 reactors, facilities, the companies, to shift from the chemical catalyzed to the enzyme catalyzed with the 100,000 ton, 60,000 ton, and 150,000 tons, especially this one, before our modification from this shifting from the chemical to the enzyme catalyzed process, they running for 5 years. And after the modification use our technology, they also running for already close 2 years. So now they have the comparison between the production cost between the chemical catalyzed and the enzyme catalyzed process. And they, according to their data, the energy consumption can be reduced by 70% for the energy cost. And also the consumption of methanol. You know, the methanol is the key issue of the chemical catalyzed process. The temperature is higher, and the methanol, some methanol will be evaporated loss. So the methanol consumption for each ton of the biodiesel will reduced by about 17% enzyme compared to the chemical catalyzed process. This is the process already successfully industrialized in 4 enterprises, and all the companies interested export the products to the European countries, because the European have the policy to mandate use the biodiesel blended with the diesel. So the price is much higher than in China. So the companies export the products, the biodiesel, from the waste, especially from the waste oil, to the European. And we filed 33 Chinese patents, including the enzyme, special enzyme, the process, and the key equipment, reactors, and also 6 international patents granted in more than 60 countries. I don't know remember exactly if we got the granted in Mexico, but in Colombia, in Argentina, in Brazil, we got the granted of the patent. And we also won many awards, including the first prize of technology innovation and first prize of scientific and the technology progress in China, exactly from the China Association of Petroleum Industry, and also won the gold medal in Geneva International Invention Show. And also very important is we got the Blue Sky Award in the field of renewable energy, which was conferred by the UNIDO, United Nations Industry Development Organizations, because of the research and the commercialization. And we also tried to promote the technology demonstration in the overseas countries. Especially, we have the close cooperation with Brazilian enterprises and universities. Also with Malaysia, we signed the agreement to demonstrate and commercialize the technology in Brazil and in Malaysia. And we create the China-Brazil Center for Climate Change and Technology Innovation. Also, another one is the China-Latin American Joint Laboratory for Clean Energy and Climate Change. And this was some median advertisement talk about our Center for China and Brazil. Since 2011, I think, we started the cooperation with the Brazilian partner, the Federal University of Rio de Janeiro. We created the China-Brazil Center together with them. Before our communication, the university already set up a pilot plant for the chemical catalyzed process demonstration of biodiesel. So we talked to them, all the equipments can be directly used. You only need to install a new reactor and another equipment to recycle the enzyme. We have the collaboration. We got the financial support from the Brazilian Minister of Science and Technology. We sent the students from China to Brazil to help them finish the demonstration. And we tried many kinds of the waste oil from the restaurant, from the industry of Brazil. And this cooperation between China and Brazil as a typical case was selected by the United Nations offers for South-South cooperation. So they selected this cooperation as a typical case for the bioeconomic South-South cooperation and then triangular cooperation in accordance with the Paris Agreement and the 2030 Agenda for Sustainable Development, which was published, this report was published during the COP25, which was in Paris or in somewhere. Now we have a team to work together with the Brazilian partner to visit many Brazilian partner industry biodiesel producers. For example, the Fiagro, which is located in the Mato Grosso state of the Brazil. They have the biodiesel production over there with the capacity 200,000 tons per year, directly use the refined the soybean oil. So we say we can change, modify this, and then you need to to refine the soybean. Time is yeah. And so we finished the design for the optimization of the process. And before the pandemic, just because of the pandemic, this progress is delayed. I hope the next year, the next year, we can put it into running of this system. And this year, April, our team, Ms. Zhao and Ms. Zhu, visited another big potential partner. It's a the name of the company is GBS. GBS, the Brazilian company. GBS is a very big company to produce the beef, to kill the yes, candles to get the beef, and they get many of the waste oil. Yeah, so get much of the waste oil. So they set up some facilities to convert the waste oil to the biodiesel. But the problem, the waste oil had high content of the moisture, high content of the free fatty acid. So it's difficult to use the traditional chemical catalyzed process to convert it to the biodiesel. So they very like to use our technology to convert the so lower quality oil to the biodiesel. So, and this guy, Ms. Zhao and Ms. Zhu, right now they went to Brazil to identify the details of this and even bring some sample of the enzyme to demonstrate it to the partners. And we also helped the Chinese company, the Sinochem. Sinochem is a huge company. It's they have very big business in Brazil. So they signed a contract with our partner, the Federal University of Rio de Janeiro, and also use the technology, the facilities to demonstrate the convert of the waste oil from the corn industry. The corn industry also gets the waste oil, so to produce the biodiesel. The third part of my presentation is biochemical synergistic catalysts for the lignocellulose conversion. The biochemical mean actually the biorefinery technology should include in the chemical, physical and biological combination together. This is inclusive, not only the declusive. So we say here is catalysis or catalyzed and chemical catalyzed synergies together to help the lignocellulose conversion. Yeah. So we, my group, the Dr. Xuebin Zhao, he is in charge of the process. We studied the pre-treatment of the lignocellulosic materials, lignocellulose, for many years. We developed a new facilities and the new process for the pre-treatment of the lignocellulose, which have the high efficiency and then can get after the enzymatic hydrolysis, we can get a very high concentration of the sugars. So because of our research days, the British company, British petroleum company, they actually 10 years ago, they invested so much money to develop the so-called second generation ethanol to use the lignocellulosic materials to produce the ethanol. So they developed the high efficiency, the yeast, which can simultaneously convert the C5C6 sugar to the ethanol. So they also developed a very high efficient enzyme for the sacrification of the cellulose. So they came to Beijing, talked to us, requested to cooperation with us. And with the cooperation between BP and my group, we developed a full flow process package for the production of fuel ethanol from straw. The total cost of cellulosic ethanol was estimated as from the $500 to $1,000 per ton, depends the cost of the feedstock, the cellulosic materials. And this was some equipment for the pretreatment for the enzymatic digestion of the cellulose at high solid content, as I say, and the fermentable sugar concentration after the hydrolysis, the fermentable sugar concentration is higher than 150 grams per liter. So which is very good for the ethanol fermentation, can get a higher ethanol concentration, and you need less energy to the evaporation. And we also developed a new technology for the production of aviation biofuel. This is so-called sustainable SAF, sustainable jet fuel, SAF, from straw, in conjunction with the component separation of the conversion of lignocellulosic materials. The hemicellulose from the lignocellulosic materials, the biomass, the hemicellulose will be converted to the xylose. You know, xylose can be used to convert to furfural, and the cellulose, of course, will be hydrolyzed to the glucose. Glucose can be fermented to the 2,3-butanediol in our laboratory. We already commercialized the process. So the butanediol, 2,3-butanediol can be dehydrated to the methyl ketone. Methyl ketone can be organized, react with the furfural, and then got such chemicals. These chemicals can be oxygenated to the hydrocarbon jet fuels by the hydrogenation and oxygenation to the hydrocarbon jet fuels. This research got the financial support from the Malaysia government, and also we got the financial support from the Norwegian government, the North European countries. And another interesting research is about the new technology for fuel cells by directly using biomass. We learn from the respiratory electron transport chain. We developed such a chain, construct an artificial electron transport chain to increase the kinetic rate of lignin oxygenation by air. So the lignin gives the electron and then become to the oxidized lignin. And after the artificial electron transport chain, finally the electron will give to the air oxygen, and then got this. This is the chemical, but by the design of the artificial electron transport chain. And such a design to increase kinetic rate of lignin oxygen by air. If directly use the air to oxygenate the lignin in the mild conditions, it's so difficult. So we already developed such a chain, and use this, we can directly use the power generation. For the power generation, you can for the lignin and from the lignin and the mild conditions, which is highest level, reach the highest level of the battery power density as reported. You can find the papers. And through this mechanism, we can carry out the controlled oxidative depolymerization of the lignin for the production of aromatics, the oxygenation of lignin into the aromatics, aldehydes, and then the antioxidant products. You can find more details from the papers like this. And the typical application for this research is this: the production of bio-based chemicals by comparing the bio and the chemical catalyst. So the major important component is HMF. You know, the HMF is a plant form for the biochemicals. And traditionally, the HMF can be dehydrated, can be production by the dehydration of glucose and also the fructose, but the yield is totally different. If directly use the fructose by the dehydration, the yield will be more than 80% about. If we directly use the glucose by the dehydration, we'll get the HMF, the yield is only half of the fructose. But you know, from the glucose to the fructose, it's already so huge industry capability, to produce. It's the enzymatic conversion, the assimilation. But the assimilation is reversible. The balance, the concentration of the fructose is only 42%. So the key issue is because the fructose is much expensive from than the glucose. So the key issue is we use the enzyme, the assimilase to assimilate from glucose to the fructose. And then this is a mixture, half and half. So the second is the chemical catalyzed dehydration of the selectively to dehydrate the fructose to the HMF, but keep the glucose the same, and then back to the assimilation again. The whole process was researched and combined in our laboratory. So the catalyst used for more than 150 cycles without the loss of activity. And the yield of the HMF, more than 80%. The convention convention ratio of the fructose is very close to 100%. And it's interesting, finally, after the convention, it's very easy to purify the HMF. The HMF recovery rate more than 95%, and the purity is 95 to 99%, just by the simple purify, and the product with the chromatography you can find is a very high purity. So the production cost of HMF could be reduced at about 50% from the glucose than from the fructose. So we emphasized again, the so-called biorefinery not mean only use the biocatalyzed process. We should combine and optimizing the chemical, physical, and bio process technologies together. So this is the idol. And also, we use the idea, the fuel cells, the electricity catalyze process to the other chains of the development high selectivity oxidation of. We also to use the electrical catalyzed oxidation for the HMF to the FDCA, or from the furfural to the carboxylic acid. So especially from the HMF to the FDCA. FDCA, you know, FDCA is now is so attractive to the chemical industry, because now the plastics, the textile polyester, the fibers, they use the PTA. You know, PTA is C6, the bone zinc, and then use the two complicated. Oh, okay, 5 minutes. Okay, and so we finished this. Also get the very high purity of the product of the FDCA, and now we are negotiating with a Chinese company to finish to start the pilot plant demonstration for this process. You can find more details from the papers. Yeah. Finally, I will talk about the fourth department, the fourth outlines of the development of a novel bioreactor with high efficiency, which this subject was, my group researched this for more than 30 years, starting from my PhD thesis. My PhD research is for the development. My background is a chemical engineering. So we research the chemical reaction, the reactor design. So that all the biochemical process convention, you can use the synthetic biology to engineer the bacteria to get a high efficiency cells or catalyst. But the final product is to fermentation. Use the fermentation to produce the huge product. So the fermentation, you have to use the bioreactor. So this is normally the biochemical reaction at the mild conditions. It's slow, the convention. The fermentation lasts for 2 years, 2 days, 3 days, or even 10 days, some products. So the energy cost is also very intensive. So we have to design a new reactor with the high efficiency. Traditionally, the fermenter is like this. You know, it's continuously stirred, mechanically stirred reactors, and the mechanical stirration have a damage to the cells, and also the major problem is the energy cost is too high. So some people actually 20, 30 years ago, some people proposed that another reactor for the airlift reactor. But traditionally, the airlift reactor is without the agitation, mechanical agitation, but it brewed the air, the gas into the reactor and steadied recirculation for the fermentation. And we can also like this. So my research on our my PhD degree thesis is to develop we can alternatively to exchange this one to this one and in time. So enhance the mass transfer. This is the idea. And another problem is use the airlift reactor, because you want to enhance the circulation. So you need a high ratio of the height to diameter. Normally, the diameter is the ratio of the height to diameter ratio should more than 6 at least. The industrial production, they use 10. The ratio is 10. If you use so high, the energy to sprue the gas is also great. So we developed another concept. We can use the multiple draft tuber with the concentric reduce the ratio H to D. So this is our idea to prove this. As I say, the drawbacks in conventional airlift have the two: steady state process, no gas hold up in downflow region, and we can use the oscillation operation to enhance the mass transfer efficiency, and also by using the multiple concentric draft tubers to reduce the HD ratio from more than 6 to less than 3. Why choose this? If less than 3, we can easily to change the traditional stirred connector. Yes. We finished use the CFD for the simulation and the optimization of the reactor from the 5 liters to the 40 liters to the 2,500 liters. Now we are trying to optimizing the 200 cubic meters. So this is some optimization of the simulation, the airlift reactor. Now this reactor already used for our 1,3-propanediol production. So our idea is to combine with the other bioproducts to promote the application of such equipment in the biochemical industry. So we have this is the traditional stir, CST fermenter, imported from Germany. And we manufactured one, have the same outline. And inside have 3 draft tubers and compared with this. And then we also scale up to the 2,500 liters. This is the CSTR fermenters. This is you can find without the agitation, we use the airlift reactor. And now this is 2,500 liters. And now we is constructing the 200 cubic meters for the fermentation. So we hope it can be expand the application in the chemical industry. Thanks.
Thank you very much. It's a very interesting lecture as always. Tenemos tiempo para una pregunta porque tenemos que desalojar el salón porque viene otro evento. No sé si alguien tenga una pregunta. Que recuerden que también va a estar acá el profesor en la tarde a las 4 de la tarde, hoy mismo, por si quieren consultarle algo. Y no sé si tengamos algo en línea. Pues bueno, entonces, there are no questions, but they are aware that you are coming back 4 p.m.
I can leave the copy of it.
Okay, él dejará la copia de la presentación.
Email and something, yeah. Sorry. So I can leave the copy of my presentation and yeah. Sorry, I can take more time and expectation, yeah, okay.
En nombre del Instituto de Ingeniería de la doctora Rosa María Ramírez, le damos un reconocimiento al profesor Liu por your excellent presentation. Thank you very much. And this is, yeah, and here is a little present from us.
Thank you.
Un aplauso, por favor. No, muchas gracias. Los esperamos en la tarde a los que puedan asistir.
I came here for looking for more cooperation between China and Brazil and Mexico, the Tsinghua and UNAM. So I hope we can develop the more opportunity for the cooperation, not only in the biochemical, for the environmental engineering and the other academic and research development cooperation. Okay.
Bueno, muchas gracias por todo. Afuera sigue el café y creo que siguen unas galletitas. Muchas gracias. Thank you very much. I'm so sorry because of the time.
It's okay, it's okay.
And they are going to make you an interview for our social media. So it's okay for you?
Yes, of course.